So because we've been doing more work in surfaces and with parameterized surfaces and parameterized functions of multiple variables, I think now is a good time to pause and do a very brief review on some of the fundamental ideas in partial differentiation, because this will become very useful to us in the very, very near future. First of all, partial differentiation, as a reminder, is a way for us to calculate derivatives of functions of multiple variables. So possibly multiple variables as inputs, possibly multiple variables as outputs as well, or multiple coordinates as outputs. And so this is really for any function of the form, right, f as a function from Rm into Rn, where m and n can be any positive integer. So as an example, right, if we have this function f of x comma y comma z equals x times the sine of zy, this is a function that takes 3 inputs, right? So its input is an element of R3, and then the output is just an element of R1, because there's just a single object as an output. As a total aside, most of the objects that we've been looking at up to this point in the class, these parameterized curves or parameterized surfaces, are functions into R2 or R3. And maybe sort of concretely, if I have a function like a curve, x of t equals cosine of t comma sine of t, right, then that's a function from R1 or a subset of R1 into R2, because it had a single input t and it had these two outputs. Right, so all of these functions, though, right, if they're differentiable, and in this class most of our functions will be differentiable, then we can calculate derivatives or partial derivatives appropriately. Right? When we just had one parameter, we just took the regular derivative of each component. When we have multiple variables, to take a partial derivative, we just take the derivative of that one variable, treating every other variable as if it is a constant. So if I wanted to take the partial y derivative of this function, right, the partial y derivative would be, first of all, as far as notation goes, we would typically denote it either as f sub y or as, let's get that right, as partial f partial y. Right? And either way, this would become the expression that we get by taking the derivative with respect to the variable y while treating x and z as if they were constants. So in this case, that would be x times sine, wait, I'm taking the derivative, not just rewriting it. Right? This would become x, because x is treated as a constant, times, and then the derivative of sine is cosine. And then to take the derivative of sine of zy, we have the chain rule in effect. So this becomes cosine of zy times the y derivative of zy. In other words, just times a z. So our ultimate answer in this case would be the partial y derivative of this function is equal to this expression right here. We also had, for functions with a single output, we had the idea of the gradient of the function. Right? And we denoted that like this. We said the gradient of f, or grad f, is just going to be the vector that includes the x derivative, the y derivative, and then the z derivative in that order. So in this case, the gradient of this function would just become 1 times the sine of zy, and then x cosine of zy times z. And then for the z derivative, we would get x times cosine of zy times y. Right? And so those are our basic partial derivatives of this function organized in this form, which we called the gradient. OK, to take an example that maybe hits a little more close to home with parameterized surfaces, we could take an expression that looks like this. And this expression can be thought of as a function, x from R2, or a subset of R2, into R3, right? Because it has two inputs, two components, u and v, and then it has 3 outputs, an x component, a y component, and a z component, each in terms of u and v. So if I really wanted to, I could treat these as individual functions, x of u, v, y of uv, and z of uv. right? And then more broadly, this is a function into R3, from R2 into R3. So a lot of our parameterized surfaces will take this form, right? For maybe not all of R2, but at least a smaller piece of R2. And then this is giving us a parameterization of a coordinate patch. Now, in order to take these derivatives, right, what we would do is we would take the derivatives of each component in turn. So if I wanted to take the u derivative of x, I would get x sub u, or equivalently, partial x, partial u. And then I would take the u derivative of this, so that's 2uv, the u derivative of this, so that's 8v, and then the u derivative of this is just 1. And then similarly, the v derivative, aka partial x partial v, will be just u squared times 1, 8u times 1, and then 1. Now there's an important sort of associated object with this that's similar to the gradient that we saw on the previous slide. And in this case, this object is called the differential of our function. Right? So let's move over here a little bit. Right? The differential of x is a matrix of partial derivatives and it's organized as follows. It's a matrix of partial derivatives, and it will ultimately contain all of the partial derivatives from all of the components. So with 3 different components and 2 variables for which to compute partial derivatives, we would end up with 6 entries in this matrix. This matrix is going to be a 3 by 2 for this example. So this is going to be a 3 by 2 matrix. And in essence, I'm going to take each of these entries as a row, and then that row will correspond to the gradient of that entry. So maybe put in a slightly more succinct way, the top row of this matrix will be the gradient of this first component. So first the u derivative and then the v derivative. So I would get 2uv and then u squared. The next row, the middle row, will be the gradient of this u component. So that was 8v, 8u. And then the final row will be the gradient of this third component. So that's going to be 1, 1. Right? So every column, right, is corresponding to a derivative, a certain kind of derivative. So I guess this column is corresponding to our u derivative. This is corresponding to our v derivative, while each row corresponds to a gradient of one of these given components. And taken together, this contains all first derivative information about this given function. Just a few sort of quick follow-up remarks. Yes, perfect. Right? Sometimes I will shorthand write this as x sub u and x sub v. And each of these is supposed to indicate a column here, right? So this is indicating the column from x sub u. Because indeed, what I've really done is I've taken my x sub u, my partial u derivative, and then written that in a column form here. And then similarly, x sub v, because I've taken this, written it in a column form. So this gives me like a nice shorthand way to write this differential. And then finally, just to point out, the dimensions of this matrix were determined precisely by this function here. And because this was a function from R2 to R3, this became a 3 by 2 matrix. And so that's where those numbers are connected. Now I mentioned the differential. Oh, and I apologize. I should really say we use certain notation to denote the differential. We use 2 pieces of notation kind of equivalently. This just depends on textbook and who's writing. But some textbooks will write this as partial f for the full derivative or the differential of f. I guess we've been talking about an x, so let's say dx. Or some will use a capital D and just write it like this. And both of those are totally fine, and we'll use them each more or less interchangeably and try to get comfortable with both of them. Now, I say that to remind you of the multivariable chain rule, this super awesome generalization of the Calc 1 chain rule, which really says to compute a full differential of a composition of functions, what you can do is calculate the differential of each function individually and then perform matrix multiplication. The sort of amazing fact is that if I want to take a composition of functions and then compute that matrix, I can compute the differential of f that's a matrix, the differential of g that's a matrix, and then multiply them together to get the right differential of the composition. And, you know, given how hard matrix multiplication is and the fact that two matrices of different sizes or incorrect sizes might not even multiply, it's pretty magnificent that this works the way that it does. All right, let's see an example of this. Yeah. All right, let's see an example of this. And so for this example, we are going to look at one that will be very helpful for us in the near future. We are going to compose a parameterized curve into R2 with a parameterized surface into R3. And so specifically, I'm going to be looking at two functions, two vector-valued functions. I have my c of t, and that's going to be going from some interval into two-dimensional space. And then I have my x of u comma v, and that's going to be going from two-dimensional space for my set u into three-dimensional space over here. And so in particular, what I'm going to do, right, I'm going to maybe first specify that for this composition to work, I need to make sure that the image of my curve actually goes into the set u, right? So let's say, maybe I should draw this. Right, so maybe the image of this curve, this parameterized curve, is here inside the set u. What I'm going to do is I'm going to compose these functions together, right? And send my function, or create the composition that takes elements of t, maps them into u, and then maps those elements into three-dimensional space. And so let's reorganize this board really quickly to sort of see what that would look like. Okay. So this is going to be my composition, right? It's going to be the composition that takes elements of I, sends them through C into U. So again, right, we had this sort of curve here. And then takes the entire, like those set of points through X and sends them over here. Right, so maybe we have our curve that sort of looks like this, maybe goes over the edge there, but we have this curve over here, and I will call this curve gamma of t, right? And gamma of t is a function from t, our interval into R3, and it's specifically organized so that gamma is equal to x of c of t. Right, so we got to get the order of that written correctly. X of c of t. We'll send things first through c, and then in the outer parentheses through x to get them over here. So with this in mind, gamma of t equals x of c of t, we can ask the very valuable question, what is gamma prime based on this setup? All right, so we might be interested in calculating gamma prime. We've already seen that we're interested in that to calculate tangent vectors to gamma and to our surface. What does the multivariable chain rule have to say about this? Well, let's take a look. Right? So what we have here is our curve c of t, which I've rewritten using its component form. So c of t has a u component and a v component, both functions of time. And then x of u comma v will have three output components, an x, y, and z component, which are functions of u and v. So these were my original sort of bigger functions, which I'm now trying to compose together. So to calculate the derivative in a semi sort of effective manner, in a reasonably effective manner, what I can do is I can calculate the differential of c, right? And so let's calculate dc. That is going to be a 2×1 vector, right? And specifically, that will be u prime of t and then v prime of t. All right, so far so good. We will then calculate the differential of x, right? And the differential of x will again be a 3×2 vector. This column will be x sub u, x sub u, y sub u, z sub u. And then this column will be x sub v, y sub v, z sub v, right? So that each column corresponds to a certain kind of derivative, and each row corresponds to the gradient of one of our three components. Perfect. Now, the composition function that we're talking about says that we would need to compute the composition, to calculate capital D of gamma, right? That's capital D of x of c. And by the multivariable chain rule, that's just dx times dc, right? Where we're doing matrix multiplication here. So let's write those down. So we've got dx, this is our sort of tall vector here, x sub u, y sub u, z sub u, x v, y v, z v, times dc, which is just u prime v prime. And by matrix multiplication, I should say, right, what we will get is a 3×1 vector. Probably need a little more room than that. A 3×1 vector in which the top entry will be x sub u times u prime plus x sub v times v prime. Right? The next entry will be y sub u times u prime plus y sub v times v prime. Okay, and then the final entry will be zu times u prime plus zv times v prime. Perfect. So each of these are a single entry, and we end up with a 3×1 vector here. We can write this another way, which we'll often choose to do. Notice that I can sort of, rewrite this by breaking it up along vector addition and scalar multiplication. Specifically, I can break this up along this addition into the addition of two vectors, right? So that would be this column plus this column. And then I can further separate out that multiplication. And I can actually do that by recognizing that each piece is sort of a clever, I see, by factoring out the scalar of u prime and v prime, right? That's going to be a common component in each vector. So in this vector here, we'll have a u prime. In this vector here, we'll have a v prime. So let's make sure that we see that in action. So I can factor this into two different pieces, right? This is xu, yu, zu, and then each of these has a u prime, u prime, u prime, plus xv, yv, zv, times v prime, v prime, v prime. All right, and I can finally, right, factor out this u prime, so that'll be u prime times xu, yu, zu, plus v prime times xv, yv, zv. So I can rewrite it like this if I want to. And I might want to do that because this object here, this column, was really nothing more than this column, right? And this column, as you'll recall, was really just our capital X sub u, right? This was the u derivative of each of our entries, but organized as a column vector. Similarly, this is just the v derivative of each of our entries, arranged as a column vector. And so I can really rewrite this entire thing as this vector, which I can call x sub u, and then I can multiply that by this u prime of t, plus this is my x sub v, multiply that by v prime of t. And so we get that our gamma prime, in this case, can be written in this nice form right here. And so we could see that by using some properties of vector addition, scalar multiplication, and our multivariable chain rule. I wanted to sort of close with this because this will end up being a relatively standard way to write these gamma primes if we set them up appropriately. And we'll see in the next video how this can help us.